Ever wonder why some AI models see a cat in a photo while others do? Or how an AI can recognize a cat in an image and in a sentence? The answer lies in how these systems think, their internal languages for representing the world. But here's the problem: each model speaks a different dialect. Today, we're exploring a breakthrough called SPARC, a tool that's helping AI systems finally speak the same language. Let's start with the basics. Imagine you're trying to compare two books written in different languages. Without a shared dictionary, you struggle to tell if they're really saying the same thing. That's the challenge with AI models. Each one has its own way of encoding information, like a unique vocabulary for concepts like cat, tree, or sunrise. This makes it hard to compare how different models understand the same idea. Enter SPARC. Think of it as a universal translator for AI. Its goal: to create a shared mental space where vision models, language models, and even multimodal systems like CLIP can align their internal representations. But how does it work? Let's break it down. First, SPARC uses global TopK sparsity. Picture this: when a model processes an image, SPARC ensures the same neurons, processing units light up across all systems. It's like forcing every model to use the same 100 words to describe a cat, so you can directly compare their descriptions. This solves a big problem: dead neurons, where some units never activate, making comparisons unreliable. Then there's the cross-reconstruction loss. This is SPARC's way of saying, hey, if Model A sees a bus, Model B should be able to reconstruct that bus from Model A's data, and vice versa. It's like teaching models to understand each other's vocabularies, not just memorize them. The result: a shared latent space where concepts like bus or balloons consistently pop up across vision models, language models, and multimodal systems. The proof: on a dataset called Open Images, SPARC achieved an 80% match in concept alignment, tripling previous methods. Imagine seeing a heat map from a vision model and a text analysis from a language model, both highlighting the same cat in a photo. That's SPARC in action. Why does this matter? It means researchers can now analyze how different AI systems really understand the world, without manually aligning their inner workings. Applications: think text-guided image editing, finding similar images across modalities, or even debugging why a model fails. So next time you see an AI misfire, remember, it's not just about training data. It's about how these systems encode meaning. And SPARC is helping us finally speak the same language. Stay curious, and let's keep decoding the AI puzzle together. But here's what's even more impressive: the models didn't just perform well on the images they were trained on, they nailed it with completely new photos they'd never seen before. Think of it like a student who doesn't just memorize answers for a test, but actually understands the material. That's the difference here. The AI isn't just spotting patterns, it's grasping the meaning behind the images. Why does this matter? Well, imagine an AI that can adapt to new situations, like helping researchers spot rare celestial events in telescope photos, or making search engines understand what you're really looking for when you type a sunset over a mountain. It's a big step toward machines that truly see the world, not just process pixels. Let's dig deeper. Researchers tested two ways AI sees the world: global TopK and local TopK. Think of global TopK as a team player. When it analyzes an image, it lights up all the relevant parts, like a detective scanning a crime scene for every clue. But local TopK: it's more like a picky eater. It focuses on some details but ignores others, leaving parts of the image in the dark. Here's the kicker: when the model used global TopK with cross-loss, a technique that helps it align text and images better, it consistently activated the right features for every concept. If it saw a kite, it lit up the tail and string. If it saw a balloon, it focused on the shape and color. But with local TopK, it was all over the place, sometimes catching the right clues, sometimes missing them entirely. This suggests that working together, global TopK, leads to more reliable learning. But how do we know the model actually understands these concepts? The researchers did a clever test. They trained simple probes to peek into the model's internal notes. Imagine a detective using a magnifying glass to see if specific neurons fire when the model sees a kite or a balloon. Some neurons were super focused, like a laser pointer zeroing in on a single detail. Others were scattered, reacting to random bits of the image. By mapping these patterns, they could figure out which parts of the model corresponded to real-world ideas. And here's where it gets cool: they visualized these activations. Picture a heat map glowing where the model looks when identifying a kite. In one example, the model focused on the tail and thread, ignoring the background. This transparency is huge. It's like giving AI a window into its thinking, helping us trust it and improve it. So what does this mean? It shows that AI isn't just memorizing images, it's learning to prioritize the right details. But it's not perfect. The balance between global teamwork and local focus is key. As AI evolves, these insights will help us build systems that are both precise and adaptable. Thanks for watching. If you want to dive deeper into how AI learns to see, hit subscribe. And drop a comment below, tell me what you'd love to explore next. Until then, keep curious.